discussing two-port networks, that is linear two-port networks, two ports which have linear components inside, resistors and control sources and so on. And we saw that because there are two voltages and two currents, we need four parameters, four numbers to describe the behavior of this. Okay. So you can think of it as an extension of a one port or a two terminal element where a single number can describe the behavior, right. When you have one port with only linear components inside, all you need to know is its resistance or conductance. Okay. In this case, there are four numbers which describe the relationships between voltages and currents. So we have two ports. This is a network N, and the voltages and currents are defined according to the passive sign convention. And we could express, for instance, the currents as a function of voltages. When we write the two port currents as a function of the two port voltages, these constants are conductances, okay, and this is known as the Y parameter set or the Y parameter matrix. Okay. And we also saw what each of these means. Y11 is the conductance looking into port 1 with port 2 short circuited. Okay. Similarly, Y22 is the conductance looking into port 2 with port 1 short circuited. And Y12 and Y21 are transfer parameters. Y21 is the current output at port 2 when a voltage is injected at port 1 with port 2 short circuited and so on, right. So, it tells you how these parameters tell you how this voltage affects this current and that current, and similarly this voltage affects this current and that current. Okay. And you can see that any element or any block that has some input and some output lends itself to this type of description, like the amplifier, right. That's what I gave the example of yesterday. If you have something, if you have an amplifier, this could be, for instance, the input of the amplifier, and this is the output of the amplifier. Okay. So, in general, anything that has one input and one output lends itself to this, and of course, you can generalize from here to higher number of ports. Okay. So, essentially, if you had a one port, you would specify its resistance or conductance, and in case of a two port, you specify the Y parameters or any other set of parameters we saw. Depending on which one you choose as a dependent variable and which one you choose as independent variable, you can have different sets of parameters. Okay. And what you do with these parameters? Yesterday I gave a numerical example, but let us do this now. Let us say we have a network N and we have a source connected to port 1. Source meaning it is a voltage source in series with a resistance. It is a pretty common representation of a source, and the two port itself has parameters Y11, Y12, Y21, Y22, and on the other side, let us say I connect a load resistance. Okay. And what I want to know is the output voltage by the source voltage Vs. What is this going to be? Please calculate it. When Y parameters are given, these are the equations, right? V is the independent variable and I is the dependent variable. It is like the conductance, that's all. And then we have V1 and I1 here. What is the constraint we get because of what is connected to the Vs minus V1 by Rs equals what? I1. Okay. And what is the constraint we get because of the output? What is connected here? Huh? Yeah, I see so many of you writing V0 equals I2 RL. Is this correct? Yes, minus I2 RL. Obviously, I mean, it's not that the voltage drop will be the same way if current is going this way or that way, right? So, V0 is minus I2 RL. And you have to eliminate V1, I1 and I2 from this whole thing. And you will be left with basically Vs and V2. V0 is the same as V2. So, that's what you want. Okay. What is the answer you get? If you combine this and this, you will get okay. And if you combine this and that, you will get right. So from here you will get so it tells you that V1 is minus V2 times Y22 plus 1 by RL divided by Y21. Is it correct? All I did was take it to this side. So now we can eliminate V1. So Vs by Rs equals 1 by Rs plus Y11 times this thing, which is V1, 1 by RL plus Y22 divided by Y21 plus Y12 and this whole thing times V2. Okay. And from this we will get V2 by Vs to be in the denominator you will have sense that Y21, which is the parameter that transfers something from port 1 to port 2, is the dominant thing that you see. Okay, but one thing I saw, first of all, this writing V2 equals I2 RL. I mean, if you make this kind of mistakes, I think you will not be able to do circuit analysis. You have to mind the directions, and when you mark the voltages and currents, mark the polarities correctly, right? Don't just say V1 okay. And also, I mean, this is just eliminating variables from a set of linear equations. You should be able to practice more and do this more quickly. This can't be taking so long. Okay. So, this is just an example calculation. Right now, this doesn't make any sense. It's some expression. But later, when we see circuit representation of two ports and so on, it will make more sense. Okay. Any questions? So, this is how you carry out calculations if your circuit contains a two port, right? Your circuit can contain simple elements like resistors and control sources and so on, or it could have a complicated box whose description is given in terms of the two port parameters. Okay. So, this, by the way, as I already mentioned yesterday, these are Y parameters or admittance parameters. Have you heard this term, admittance? Yes or no? No? Okay. So, it's basically a generalization of conductance. Have you heard the term impedance? What is it? Huh? No, that's okay. But where, in what context have you heard the term impedance? Yeah, so basically it is like resistance. It's the ratio of voltage to current, but when applied to storage elements, right? Also, when you have resistors and capacitors. So, this admittance is the same thing. It's analogous to conductance. It's the ratio of current to voltage, but not for a resistance, but I mean not only for a resistance, but for storage elements like capacitors and inductances. Okay. So, clearly this Y is the ratio of current to voltage, right. So, if I had to write this, the vector current vector equals the Y parameter matrix times the voltage vector. So, this looks like if you had a simple element, you would have I equals G times V, where G is the conductance, right. So, this Y parameter is analogous to conductance, okay, and we have other sets of parameters. Any questions about this? So, the calculations, I mean, you will have more equations, but it's still a set of linear equations which you should be able to solve, okay. And keep in mind that in this description, for the two port, we have passive sign convention, right. We have V1 and I1 going into that, and V2, I2 going that way, okay. Now, when we have a one port with only linear elements, no independent sources, what is the simplest equivalent between the terminals? It's a resistance or a conductance, right. So, if I had to make a circuit equivalent, it would just be a conductance or a resistance, okay. By the way, when I mark resistors, I will mark either the conductance or the resistance value next to it. It's assumed from the context which is which, right, from the units in case of numerical values, or from the symbol it should be clear which one I am marking. Now, for the two port also, I would like to make a circuit model, right. I mean, sometimes that's more useful to visualize things and so on. This representation is more abstract. So maybe I would like to make a circuit model of this, right? Just like whatever circuit is here, I could represent it by the single number, but what is it? Electrically, it's a resistor, right? Similarly, I would like to make a circuit model, simpler circuit model than what is actually inside, that is generally applicable and that will follow these equations. Okay? You understand what we are trying to do? So, I have V1, I1, V2, I2, and in here I want to insert some circuit elements so that it follows this relationship. So, what should the circuit elements be? Give me suggestions. Basically, I want you to make a circuit as simple as possible that will follow these equations. What would that be? And you can use any of the elements that we have discussed so far, right? Resistors and control sources and so on. Please do this. What is that? Resistance and a? Where should be the resistance? Yeah. So, there should be a conductance Y11 across 1 prime, right? So, what will be the current flowing through this? Y11 times V1. So, that will contribute this portion of I1. Okay. What else? Yeah. So, all we are doing is simply we have a sum of two currents. Okay. So, we have to put two things in parallel. Now, the first one, it is a current that is proportional to V1 itself. So, it will be a conductance of value Y11. The second one, it is a current, but that is dependent on voltage elsewhere. So, it has to be a voltage controlled current source. The value of the voltage controlled current source is just Y12 V2. Okay. What about the other side? Huh? You will have a conductance of value Y22 and a voltage controlled current source of value Y21 V1. Okay. So, this all we did was for each of these terms we added an element, that is all. Okay. It is also quite common to use this model. I mean, it looks like a circuit and it is easier to analyze when you have it in circuits. So, this is the circuit representation of a two port. Yeah, that is fine, because it follows these equations. So, that means that whichever circuit follows the same equations, it will give the same solution. Now, there is one particular problem with this which I highlighted, that actually somehow this is how in every book a two port is denoted, right. It has 4 terminals, but a 4 terminal network, how many unique voltages and currents do you have? If you have 4 terminals, how many unique voltages and currents can you define? 3, right. You have 3 currents, the 4th terminal will have the negative sum of the 3 currents, and similarly you have 3 voltages. Let us say you take one of the terminals to be common and there will be 3 voltages from the 3 terminals with respect to the common terminal. But this is not a generic 4 terminal element, this is actually 2 port. That means that we can apply a voltage here and there. Okay. So, that is why this type of floating stuff comes in. Now, we will see later a 3 terminal 2 port, okay, where the two ports have a common terminal. Okay. So, this is 1 prime and 2 prime, 1 prime and 2 prime are the same. In this case, everything will be well defined because we have 3 terminals. So, that means actually we have 2 voltages and 2 currents, and that is consistent with the 2 port description. Okay. So, in this case, I mean there are actually some weird cases where this kind of thing may not work very well, this representation. Okay. That is because actually this is not a, I mean somehow this is how a 2 port network is shown in a generic form in most of the books. Okay. But for instance, by connecting a voltage source between these two, I mean if you see a terminal, you can always do this, you may run into some problems. Okay. The 3 terminal 2 port does not have any such problems. Okay. But for the cases that we will see, these things will work, so it is okay. By the way, I mean while they are physically disconnected, there is no line connecting them. I mean there is connection through the parameter, right. So, this voltage is coupled to this side by Y21 and so on. So, that part is okay. No, that is what, you can't necessarily do that. I mean if you have an arbitrary 4 terminal network and then you connect, let us say this and that, then you will have a problem. Okay. Maybe if we have time, we will see examples of that. What is that? Yeah. So, if we had a, that is right, I mean if we do connect it, it will become 3 terminals, but in the actual circuit this and that may not be connected, or if you connect it, let us say for instance you have a resistance here between these two, okay, and if you connect it, it shorts out the resistance. Okay. So, that is why actually I do not like this this kind of description too much, but because it is used very commonly, I will use that. So, in reality, if you have 3 terminals, you for a 2 port you should have 3 terminals, right. With 4 terminals you should legitimately define a 3 port. Any other questions about this? So, basically when you have these 2 ports 2 port network, you can describe it with 4 numbers which are called the 2 port parameters. If you choose voltages to be independent variables and currents to be dependent variables, you will have Y parameters. Okay. And for every parameter set, there will be an equivalent circuit, right. For the Y parameter description, this is the equivalent circuit, because the Y parameter description, you have I1 composed of 2 currents, one due to V1, one due to V2, that is represented by 2 elements. This represents the current due to V1, this represents the current due to V2. Okay. Similarly, here this represents the current due to V2 and this one due to V1. Okay. And sometimes instead of fooling around with the equations, you can put this circuit in place of this network, and many things become kind of obvious. Okay. It is just a different representation of whatever the equations are saying. For instance, let me go back. I mean again this example does not make too much sense right now probably, but let me use the circuit description here. And we saw that V2 by Vs was now. I keep saying this, I have said this earlier also, whenever you get an expression you should do a sanity check to see whether the terms have come out right or not, because I mean you look at this, there are so many terms, who knows whether it is correct or not. But by looking at this particular circuit equivalent, you can see why some terms come out the way they do. Okay, what are they? I mean, there are some terms in the expression for V2 by Vs, and if you look at the circuit, it's very obvious why it comes out the way it does. Which terms am I talking about here? Yeah, why does it come out that way? You are saying the first term in the denominator is sum of conductances Y11 and Gs, right? Why should they get added up? When will conductances get added up? Huh? What's that? No, I mean when do resistances get added up? When do conductances get added up? Huh? Parallel connection. Okay, do you see a parallel connection here? Yes or no? You don't see any parallel connection? No, if you add up two conductances, that means that those two conductances are in parallel. Are they in parallel in the circuit? Huh? Or any conductances, are they in parallel in the circuit or no? Which ones? Clearly, these two are in parallel. Okay, so you expect that those two will come together, isn't it? What about this? What is an equivalent of this? What is an alternative way of representing this? Yeah. What's the value? Vs by Rs and Rs. So they are indeed in parallel. Okay. So these two are in parallel. That's why we get that. These two are in parallel. That's why we get this. Okay. And actually, if I write just the expression for V2, I'll have Y21 times Vs by Rs, which is actually the input current, right? This is the current. So if I had called this Is would have appeared here. Okay. I mean, I started off with a circuit which had a voltage source, but imagine that I had some current source there, Is. Obviously, everything had to be proportional to Is, isn't it? So that should appear. So that basically should make as much intuitive sense out of the expressions as possible, right? That increases the chances of the expressions being right. Okay. Why does this sign come out negative here? Huh? Why does the sign come out negative? Which way are the currents flowing? Which way is the current flowing in the load? This one is pulling current, isn't it? From the load. So obviously it will develop a voltage something like Y21RL in this polarity. Okay, it's not Y21RL, it's Y21 divided by Y22 plus 1 by RL, but that's what you get. Okay, so it's just because of the direction of this current source. Okay, so all these things you should notice. I mean, when you solve problems for practicing, it's not just some dumb practice, right? That's why I say that solving like 1000 problems of the same type without thinking doesn't buy you anything. Okay, you solve enough problems so that you become fluent, but at the same time you have to be like more thoughtful. There has to be like more quality to the practice. You should think about why every step gives you the answer the way whatever answers it does and so on. Okay, otherwise, I mean, you will learn the mechanics of it, but anytime you see something new, you will get confused. So, I wrote this just to illustrate the value of the circuit equivalent. So, similarly, many times it's very obvious to see what is going on in the circuit if you use the circuit equivalent rather than the equations. I mean, I think you know already that there is value to representing the same thing in many different ways, because some phenomena become obvious in some representations and not in others and so on. Okay. Any questions so far? So, the same network N So far we looked at Y parameters. So which says the currents I1 I2 equals the Y parameter matrix times that. Now this may or may not be convenient for the particular device at hand, just like in some calculations using conductances may be convenient, in some other calculations using resistances may be convenient. Okay. So maybe elsewhere I would like to make currents the independent variable and voltages the dependent variable. In that case, I will have a different set of numbers. What will be the dimensions of these numbers? Resistances. Okay. So this is called the Z parameter set, or thanks, impedance parameters, right? Because it's like a resistance, that's all. Only thing is, now we are looking at the relationship between the current vector and the voltage vector, not just a single, scalar current and a scalar voltage. Okay. Now it's the same network. So obviously the Y and Z parameters are related to each other, right? Because the same network can be represented by either. What is the relationship? What is the, how if I gave you Y parameters, how would you get the Z parameters? Yeah, just inverting, that's all. Okay. So in this case it's very easy. Invert the matrix. And what is the inverse? What is the determinant? And what will be the entries here? Yeah. Okay. So because calculations are convenient with one or the other, you should also be able to move between parameter sets. And these relationships, once you figure them out, you can keep a lookup table and then look them up, and you can always rework them if necessary. Okay. You can also, as an exercise, try to do this, calculate V0 by Vs with Z parameters. Okay. So that you can do by yourselves and see how that expression, whether it looks similar or different from the other expression. Okay. Any questions here? This is just an alternative representation, that's all. It's just like first we looked at conductance or the Y parameters, now we are looking at the resistance, right. And sometimes you don't do either, maybe you will have I2 and V1 as the dependent variable and I1 and V2 as the independent variable, and this particular set of parameters happens to be called the H parameters, and H stands for hybrid. Right. What will be the dimensions of these? Conductance or resistance. What's the dimension of H11? Sorry, I mean, I shouldn't write it like this, it's always that way. Okay, port 1 and port 2. H11 is resistance. Basically, it is V1 by I1 with the second port short circuited. Okay, so this is the resistance looking into port 1 with port 2 shorted, right? And what is H12? It's a dimensionless number, right? So it is V1 by V2 with I1 being 0. H21 is the current gain I2 by I1 with the second port short circuited. And finally, H22, what is it? What is the dimension of H22? It's a conductance. It is I2 by V2 with port 1 open circuited. Okay. This is why it's called the hybrid parameter, because the parameter set contains resistance, conductance and dimensionless numbers. And the last one is with these two interchange, that is I1 and V2 are dependent variables and V1 and I2 are independent variables. Okay. And for whatever reason they chose the letter G for this. Okay. And these are called the G parameters. And as expected, here also you will have a combination of conductance and resistance, okay, and dimensionless constants. Is this fine? The same two port is described by all these things, okay. So that's a little bit tedious now. So I'll just leave it as an exercise before the Monday's class. Please, first of all, draw the circuit representation for Z, H and G parameters, and also express H and G parameters in terms of Y parameters. Okay. It's just a matter of taking the linear equations you have and manipulating them so that the dependent and independent variables are what you want them to be. Okay. So please do this. We'll continue from there later.